pass them as linear programs. I'll show you how to do that at the after we take a look at an actual example here. Now, some of them might be integer linear programs, which it means that that's a very, very difficult problem. That's an NP-complete problem. Again, something we'll talk about at the end of this class. But I do want to make you aware that there are these wide variety of problems that can be reformulated as a linear program or an integer linear program. And then then you've got this entire wonderful toolbox of tools that you can throw at it. Gradient descent, simplex, which is basically the same thing in most contexts. You've got the interior point method, and you've got all these tools out there that you can pull out any linear solver that you can then apply that problem to. So to review from last time, we wrote this here. These are linear constraints. Okay, I've only shown this now with 2 variables, but of course in general you can have 3 variables, 4 variables, 50 variables. But it's only going to make sense visually if I keep it only to 2 variables. If you start writing 3 variables, then you're in 3 space and you're talking about this 3-dimensional polytope. If you're in higher dimensional spaces, then you can't even visualize it anymore because unless you're not of this dimension, it's very, very difficult to visualize 4 dimensions. So you're giving these linear constraints that cannot be violated. If these are violated, then it's not a feasible solution. Kind of like with Hamiltonian path problem, or the knapsack problem, or any other problem that we've looked at up to this point. We've seen solutions that are feasible and infeasible. And we want to only consider feasible solutions and then find the best solution there. So we're in the realm of optimization problems here. Here's an objective function. This is our objective. This is our goal, basically. We want to maximize this function. This is basically a payoff function. You can talk about maximizing profit. You can also talk about minimizing costs. You can take what's called the dual of this problem, and instead of maximizing this objective function, you can minimize the objective function. And there are lots of tricks that you can use to accomplish that. You can just take the negation of everything, and now a maximization becomes a minimization, right? Just simple tricks like that. So we'll only consider maximization here. Basically, the scenario here is that you can invest in one of 2 resources. If you've got $1,000, you can put $1,000 into X and $0 into Y. You could put $500 into each, right? There are lots of ways that you could allocate these resources and invest in these 2 variables here, each one of them with their own payouts, or in their payoffs. So to understand what this is asking about, I'm going to go ahead and graph these. Again, this is why I kept it in 2 variables, so that we could actually look at a graph of what this looks like. So here's the X, or the Y and the X axis, right? The first constraint here, that X has to be non-negative, well, that corresponds to the the Y axis right here, right? We're only looking at solutions in this direction, okay? The second one, where Y has to be greater than 0, then we're only looking at solutions basically in the first quadrant here. Anything outside the first quadrant is going to be infeasible. X is less than or equal to 9. What does that look like? Well, if I go over here to 9, and I draw this invisible Y-axis right here, right, then basically the X value here, X and Y, it has to be less than 9. So I'm constraining the space, the solution space here, basically. I've already constrained it here and here to the first quadrant. Now I'm basically cutting off a huge chunk of the first quadrant. Okay? The next one is 2y plus x is less than or equal to 12. Let me rewrite that over here. 2y plus x is less than or equal to 12. To get this into a form that looks familiar, again, it's a linear constraint, so it's going to look like a line. You can go ahead and rewrite it as y is less than or equal to, I'll take x onto the other side, negative x, right, and I'll divide by 2, so this is actually negative x over 2 plus, and then 12 divided by 2 is going to be 6. Right? This is a line. If you cover up the less than or equals and you just consider the equals, you can draw a line out of this. It's going to have a negative slope, 1/2 slope here, and its y-intercept is going to be 6. So I'll go up here to, say, 6, and I'll just estimate that. And I will go ahead and draw this invisible line here. right? And it intersects over here somewhere at 9, and this point right here is 9 and 1.5 if you want if you want actual numbers here, right? And then of course this is 0, 6 up here, okay? And the condition that y has to be less than or equal to this means that I'm only considering solutions down here. So already I've cut my solution space, which was infinite. I've cut it down to this finite region right here. The last one is another constraint here. 2y minus x is less than or equal to 8. So 2y minus x is less than or equal to 8. If I rewrite that as a line, I will get that y is less than or equal to, now x comes over to the other side, but it's positive now, so it has a positive slope, and 8 gets cut in half. And the y-intercept over here is going to be 4, and it's going to have a line that looks something like that. And again, y has to be less than or equal to this, so I'm constraining it yet over here. This right here, I don't want to shade it entirely, but it's called the feasible region. Okay? That is my solution space. Now, if I were to just be brute force about this, how many points would I have to check? How many points are in this region right here? An infinite number, right? So brute force, now we're not just talking about exponential or super exponential, factorial kind of stuff. Now we're talking about an infinite number of points that we potentially have to check, right? There's another formulation where you could look at integer linear programming. And integer linear programming means that you are constraining yourself to integral points. So if you want to, you can go ahead and draw all these points all around here. I'm not going to draw them all. But basically, this is your feasible region, but you're only looking at the integral points. 0, 0, 0, 1, 1, 1, 2, 2, 3, 3, 2, 3, etc. Anything that's in this, you'd have to check all of those points. And in general, there are going to be m choose n, which is going to be the number of constraints that you have, choose the number of variables that you have, and basically that's going to be blow up and be exponential, right? So integer linear programs, at least they're finite, but it's still going to be exponential. Remember that we are trying to maximize this objective function here. Let me go ahead and rewrite that over here. Maximize 2x plus 3y. Now that's not an equation. We can kind of make it an equation though. Let me go ahead and rewrite it. Again, I will take x to the other side. There is no other side though, right? So what I'll do is I'll take x to, I'll rewrite it like this. Y is equal to, I'll put a question mark here because again, there's no other side here yet. Oh, sorry. Is it? Oh, 4x, sorry. Thankfully, I've been using pencil. 4x, thank you. I'll take that to the other side, and it's negative 4/3 x plus, now here's why I said this wasn't an equation, right? This isn't a line. Just like if you do Gaussian elimination and you find that your last line is all zeros, it's an indeterminate system, right? You could write any old x and then any old y, and that's a solution. You can write any. There are an infinite number of solutions. There are an infinite number of lines here. If I just simply put in b here, what's the y-intercept? You're talking about lines that look like this. And it could intercept here, it could intercept here, it could intercept here, but they all have the same slope. So for example, I could write a line that intersects at this point, right? If I take x and I take y, that will determine x and y. That'll then determine b. I don't know what it is. It's going to be way up here. But it's going to look something like this, right? Because it has a negative slope. And so, here's the y-intercept. This is plus 13.5, right? B is equal to this. Well, there's one solution, and it intersects the feasible region at one point, right? I could rewrite this. I could write it over here instead, right? I could say intersect it right here. There we go. I'll just do it like that as a solid line. Or I could do it right here. Or I could check an infinite number of these lines. Now, if I'm going to brute force this, again, it's going to be infinite. I'm going to have to look at this line and say, okay, well, I look at this point and this point, this point. There are an infinite, even if I restrict it to only one line, there's still an infinite number of possibilities. Until a mathematician comes in and tells us, wait a second, if you have a feasible region, you actually only need to check what are called critical. There, I think we could use the term critical points. I think that there's another term for it. But you only have to check the points at which all of your constraints meet. You only have to check these points. And whichever one is the best point, that's the one that's going to be the optimal solution. Take a look at this line again, right? Remember that we're trying to maximize a positive objective function. If you just move this line along, right, at some point it's going to intersect the feasible region. And then if I move it further, right, if I increase it in the x direction, what happens to the y direction on the border of this feasible region? What's going to happen? It's going to go down, right? It's going positive in both of these directions. It's going positive in this direction, positive in this direction, but then 0 in the y direction. So really all you need to do is take this line and move it across until you get to a point where moving it further actually decreases the objective function value. Right? And further, you don't have to move it along every intermediary point. All you have to do is check each one of these critical points. Let's go ahead and write out these critical points. Here's a point, 0, 0. What's the value of the objective function at that point? Well, if I plug in 0 and 0, I get a value of 0. I want better than that, right? Remember, I want to maximize. Right? Okay, well, if I start there, which direction should I go first? Let's try to be somewhat greedy about this. Should I travel over here to this point and then check this point, or should I travel up to this point and check this point next? What do you think? Traveling in this direction means I'm increasing my x. Traveling in this direction means I'm increasing my y. Which one will pay off quicker? If you increase x or if you increase y? X. Why? It has the larger coefficient. It has the largest. What if I take the partial derivative with respect to x? I get 4. If I take the partial derivative with respect to y, I get 3. What do we call derivatives also? Like if I take the derivative, it gives me the tangent line. What's another name for that tangent line? Slope. That line has a slope, but it's the also rate of change. Lots of synonyms here. The one I'm looking for though is think about a hill. A hill goes down, right? Or it goes up. What do we call that? It's the gradient or the grade, right? So traveling in the x direction will give me the highest gradient because it gives me, if you just take the first derivative, it gives you the positive slope there, right? So I will travel in the x direction. What's the next point? It's going to be 9 and 0. What's the value of the function now? If I plug in 9 and 0, I get 36. We did better. Okay, well, I found an even better point here. If you want to look at this, is called a polytope. It's basically a polygon because it's in 2 space, right? You can think of if I had 3 variables, that this would be a polygon in some way, a convex polygon in 3 space. And what I would be doing is I would be traveling on the surface of this polygon. If I were in 4 space, well, now the visualization fails, but you'd be doing the same thing. You'd be traveling in one coordinate direction until you get to the next critical point. Okay? All right. Well, now I'm here at this point. Where's I can't increase x anymore. So this is going to fail me that I can't go in the x direction anymore. Otherwise, it'd be infeasible. So I might as well go in the y direction. But if I had 3 or 4 other variables, I'd do the same thing. I would take the first derivative, or just simply look at the coefficients, because this is all linear, and I would travel in that direction next. The one that gave me the best payoff for traveling along this thing. Again, x and y, I can only go in 2 directions. But if it were 3 space, I could go in x, y, or z. If it were 4 space, I could go x, y, z, and whatever we call it. We've run out of letters now, right? And I would need to look at all those. Which direction do I go in next, right? So let's go up here, and like I said, this was 9 and 1.5. And if I plug that in over here, I get 36 still. But 1.5 is going to give me 36 plus 3, 4. Yeah, what? 41.5, you said? 40.5, right? Yeah, okay, good. I'm just checking myself over here. All right, well, we've increased it as much as we can in the y direction, and so there's nowhere else to go, right? We have to go in the x direction, and because the next point is over here, we're actually going to go negative in the y direction, and that gets me up to this point up here, which is going to be 2, 5, right? But before I do that, should I travel in that direction? That's I don't know, because yeah, I'm decreasing my x value here, but I'm also increasing my y value. Right? So let's go to that point and see what it looks like. So 2, that's going to be 8, and then 5 is going to be 15, 23. What happened? You went down, right? This was your local and thus global maximum. You've maximized your value at this point, at this point. And so there's no reason to go on to that next point, and there's certainly no reason to compute this, but you can if you want to. What is it, 0.4? Well, that's only going to result in 12. You're getting even worse there. All right? This is basically the simplex method. It's a method that goes all the way back to John Nash, 40s, 50s, whenever it was created. Basically, you're greedy about it. You say, I'm on this polytope. You know from mathematics that the optimal solution is going to rely at one of these critical points. And you arbitrarily start at a point, and then you start walking around, right? This is a gradient descent, or you start walking around on this polytope. And you use a greedy strategy to determine which direction do you walk in next. Do I walk in the x direction, the y direction, the z direction, or the 4th dimension, or the 5th dimension, 6th dimension? Which one do I go to next? All it is the first derivative, or just simply the coefficients here. Right? That's the simplex method. Simplex method is not guaranteed to be polynomial time. There are some very, very bad degenerative cases where you can end up going back, zigzagging through the gradient descent or whatever, and end up doing an exponential number of point checks to see, I'll go left, go right, go left, go right, go left, right, until you actually zoom in onto an actual critical point. So it's not a full solution, but in practice, it's worked for the last 60 years. Only as recently as 1979 and 1984 did somebody actually come up with a polynomial time algorithm to solve linear programming like this. But still, simplex method is still used in practice, because in practice, for practical problems, it's extremely fast, right? And so that's why it's still used. Why is it good? Well, I mean, you don't just have generic equations like this, right? Unless you take an operations research course and then you're given all these generic equations. Okay, now maximize this and show your work and do the simplex method. Instead, you're usually given some other problem that has nothing to do with linear programming. For example, knapsack formulation. Remember the knapsack problem, where we're given n items, we call them A1 through AN, with values V1 through Vn, and weights W1 through Wn, and a capacity, an overall capacity that you cannot violate, right? This has nothing to do with linear programming, does it? At least on the surface. But we can take this problem, and where we're trying to maximize your value subject to the overall weight constraint. Right? And you can take an element or not take it. Right? So the way that we're going to recast this problem is we're going to formulate this as a linear program instead. The first thing I need to do is I need to define my variables. There are no variables here, are there? Right? There's no variable x1, there's no variable y, there's no variable z, there's no variable x1, x2, dot, dot, dot. I need my variables first for my actual integer linear program to solve. So what I'm going to do is I'm going to define xi to be either 0 or 1. 1 if item I is taken, and 0 if item I is omitted. Right? So they're binary values. You either take it or you leave it. Remember, that's why we originally called it the 0-1 knapsack problem. You can either take it or you can leave it. Right? Now, I need an integer linear program here. Instead of writing this out, I'm going to write it out as a linear program. I will, maximize a summation of my values, vi times xi, where I runs from 1 up to n. Right? Remember, these are values. So if xi, these are called indicator variables. Indicator variables. They're indicating whether or not you took the element. Right? And if it's 0, then you don't get that value. If it's 1, then you get that full value. Well, what's our constraint here? Subject to, if I sum all the weights multiplied by their indicator variables, that can be no greater than my weight capacity W. For x of I being either 0 or 1, and I running from 1 up to n. Right? That is a linear programming formulation of the 0-1 knapsack problem. And simply by reformulating it as an integer linear program, now you can take Simplex Method off the shelf and apply it and solve this other problem over here. You can take the one that was developed in '84 was called the interior point method. Take that generic solution off the shelf and apply it to this problem right here. This is what you do all the time in algorithm development. You try to see the patterns. Remember, you try to see the structure of a problem and say, I've seen that before. I can formulate that as an integer linear program, or as a linear program, and then I can use all these off-the-shelf solutions. You do this all the time in program. This is something that we try to really drive into your heads in CS1 and CS2. Don't reinvent the wheel. Right? Don't write your own square root method. Don't write your own sorting method. Use an off-the-shelf solution and adapt it. Just like, and you do the exact same thing in algorithm development. You try to see the pattern that I can formulate that as a graph problem, and now I can apply a minimum spanning tree algorithm to it. Or I can reformulate that as a linear program, and then I can go ahead and throw this linear programming solution, the interior point method, at it. Right? Some authors like to call that transform and conquer. In other words, you're taking one problem in one domain and simply transforming it into a different problem in a different domain where you've got this entire library of solutions that you can throw at it. And linear programming is a very, very common formulation that you can use here. The problem, however, is this guy right here. Right? This makes this an ILP, which is an integer linear program. Now Simplex Method fails because the argument that your optimal solution lies at one of the border regions and one of the critical points is no longer true. Was this a critical point? Was this an integer point? The best one that we found. The best one that we found right here was 9 and 1.5. Is that an integer? Nope. This only worked because we had the freedom to go to any single point in this entire region that we wanted to. That falls by the wayside. And if you've only got integer constraints, well, now you've got all these points in the interior region. and you can go in the feasible region, and you have to go to each one of those points basically, right? In other words, you're ending up doing an exponential number of point checks again, and that's what makes this a much more difficult problem. You can always relax it though. So relaxation. You can always say, well, okay, not 0, 1. I can say that x of I is between 0 and 1. This takes an integer linear program and takes away this integral constraint, that it doesn't have to be 0 or 1 anymore. It can be 0.1. It can be 1/2. It can be 1/3. It could be 1, or it could be 0. It could be anywhere in between here. That's a relaxation. We're going to take this integer constraint and we're going to relax it so that it's not so strict anymore. That expands our region back out to the entire thing, and now the simplex method can find the optimal point again. Now, does that necessarily correspond to an actual solution? No, it's in the original knapsack here. No, not anymore, because what we're doing by doing this is we're saying, you don't. Here's an item. You don't have to take all of it or none of it. You can go ahead and chop it in half and take half of it if you want. Right? That's a different problem. That's a fractional knapsack problem. But maybe you re-examine your problem and say, oh, well, actually, we don't have that constraint in this problem. I can actually adapt this into a fractional knapsack, and now simplex method will work. Right? It's all in your ability to identify those patterns and say that I can take this and I can reformulate it as something else. Or, oh, okay, that's not going to work. It's actually integral, and so I can't apply this problem to it. There are a whole bunch of problems where the integer solution corresponds to the original solution. Those are that's if the matrix is what's called totally unimodular. And there are some problems. For example, if you remember the assignment problem, when I've got n people and n tasks, and I have to assign a certain one person to one task and minimize my overall cost, that's one of those problems that is totally unimodular, and you can formulate an integer linear program to it, relax it, apply the simplex method, and the solution that pops out of that happens to magically be an integral solution. Right? So there are lots of results in this. Again, I'm only treating this in like a half a lecture. This is unto itself at least 3 courses. Linear optimization methods. I think the math department at least at one point had linear optimization 1 and linear optimization 2. They had 2 whole courses devoted to this entire topic here. And of course, you can take operations research where they touch on this. You can even have, instead of linear objective functions, you can have quadratic objective functions. Now you're talking about quadratic programs and quadratic optimization, right? So a whole huge area, right? And way more than we can ever hope to get to in, say, CS3. But I did want to show you that alternate formulation so that you can see that you can always take at least a lot of times you can take one problem and transform it into another that's not so obvious, and you can have a solution, an off-the-shelf solution for it. All right. So we've done plenty of algorithms. This course is data structures and algorithms. Let's actually do a data structure now. Right? And it's actually going to be a review data structure. Remember that we've got binary trees. Oops, trees. Right? So what's a distinguishing characteristic of a binary tree? Remember, I'm not talking about binary search trees yet, but what are binary trees? Well, what is a tree to begin with? What is a tree? It's a graph, right? We usually write them as still T is equal to a vertex set and an edge set. Right? That is, or that what? What makes something a tree? That is the acyclic. Right? It contains no cycles. Hey, guess what that means? We've got structure. If we just had a generic old graph, well, any two nodes can be connected to each other. There could be an exponential number of paths. There could be an exponential number of cycles. There could be an exponential number of a lot of things. But if we have a tree that is acyclic, then it follows that between any two vertices, how many paths are there? There is exactly how many paths? So here's A, and here's B. And the tree is connected, so there's at least one path. Can there be another path? What if there were another path? What would we have? A cycle. So there's exactly one path. All those things that could potentially have an exponential number of them, an exponential number of paths, an exponential number of cycles, an exponential number of relations, we cut those all down to one. We provided some structure here. Further, a binary tree is oriented. We have a parent, a left, and a right child. And our trees grow down, right? So this is this is a parent, and this is the left child, and this is the right child. Of course, you could have variations like this. If you a parent without any children, no children. What do we call that node? I mean, it could come up from there's more stuff above, but there are no children. What do we call that? A leaf. Right? You could have a parent with just a left child and no right child. You could have a parent with a right child but no left child. All right? What other nomenclature do we have? So a vertex with no parent. In other words, say this vertex right here. There are a bunch of nodes going down, say, there we go. What about this one right here? There's no parent here. Again, it grows downward. These are the children. This is the parent up here. What do we call this thing? The root. Okay? From the root to any node, there is one path. The length of that path from the root to any node U is the depth of U. All right? Let me go ahead and redraw this, and I'll just draw another one here. I'll call this A, B, C, D, E, F, G, H, and I. Okay? So, node, we'll just take a few examples here. Depth. What about the depth of F? What's the depth of F? 1, 2. Going from the root down to F, there's a depth of 2. What about C? What's its depth? Just 1. What about A? What's its depth? 0. All right. What about I? 1, 2, 3, 4. All right. The depth of the tree is the maximum depth of any node. Okay? And in this case, the depth here is going to be, I already gave you the deepest one, is going to be 4. All right? Here's another related concept, height. All right? What is height? Well, depth goes from the top down. The height of a node, U, is the longest path to any of its descendant leaves. Right? So again, we've got a parent-child relationship. So we've also got an ancestor relationship and a descendant relationship. So the same question here, F. If I restrict my attention to this subtree right here, F, then it's got two leaves, two descendant leaves, H and I. Is G a leaf? Nope, because it has a child. So it's the longest path, of course, the path from F to H, one of its leaves, is 1. The path from F to G to I is 2. So the length of the longest path is going to be 2. That's just a coincidence, okay? What about C? 1, 2, and you get to a leaf. 1, 2, 3, and you get to a leaf. Okay. What about A? What's the deepest node? Oh, deepest leaf? 1, 2, 3, 4. What about I? What's its the height of a leaf itself is going to be 0. Okay. So actually, it's not that much of a coincidence. Can you glean, or to use some slang, can you grok the relationship between these two? I chose A and I for a very good reason here. Flip, flip. F is right in the middle of this tree. If you go up and if you go down, right? There's some relationship between the depth and the height. I'll let you think on that one. Okay? All right. What about a binary search tree? Again, this is all just review. A binary search tree also has keys in its nodes. And in its left subtree over here, everything has a key that is less than k, and everything over here has a key that is greater than k. Right? And that's an inductive property that holds for every single node in the entire tree. What about a heap? Remember what a heap is? A heap is not a binary search tree, but it is a binary tree. It's a binary tree such that the key k in a node, we'll go with a max heap here, or let's go with a min heap. K in a node, key k in a node u, is less than both its children. So if you want to redraw this picture here, k, everything in the right subtree and everything in the right, the left subtree and the right subtree is going to be greater than k and greater than k. Right? That's not going to help us out much if we're trying to do an arbitrary search. But a heap is also full. Right? Every node is present except the last level, which is full to the left. So if you want to visualize this tree here, it's a complete full tree, full binary tree, except for possibly the last level, and all of the nodes are shoved over here to the left. Right, so it looks something like this. That's just a review. If you need some more review, I've got the CS2 book available for you. There's an entire chapter on trees, and actually I think it's in the, I repeat it in the CS3 lecture notes here. Okay? So what our goal is going to be for the next couple of days is to talk about trees. We're going to look at some more applications of trees, tree data structures, and we're also going to look at improving binary search trees because just plain old binary search trees, there's no guarantee on the depth. That was a question in your first homework. There's no guarantee on the depth, and so if you just put stuff into a tree, you could end up with a degenerate tree where if I add 5, 10, 15, 20, 30, 40, 50, all in order, I would end up with a skewed tree. In other words, there's no left child, there's only just right children, or right children, left children, whatever your perspective is, right? And if you've got that, it's no better than a linked list. Instead of drawing it oriented, just draw it like this, and you can see that it's just a linear linked list, along with all the inefficiencies of a linked list. So we're going to look at ways of improving a binary search tree so that we can kind of get this guarantee that we had with heaps, where it's pretty much balanced or full, which gives us a guarantee on the depth of order log n. Right? But before we do that, let's look at another problem here. And we're probably going to be able to fit this in the rest of the day here. First of all, we need a little bit of coding theory. This is going to be an application of trees. Coding theory. Right? So coding theory is information theory, is what it used to be called. Coding theory is not like the theory of how to code a program. That's not what we're talking about. We're talking about a code. Right? We're talking about taking symbols and encoding them. Encoding symbols. What's one encoding scheme that you're well familiar with already? Encoding them usually in binary. If I just write out a text file, well, when it displays, you can read the text. But how is that actually encoded in a computer? ASCII. ASCII is a fixed length encoding. Right? Capital A. Does anybody know what the value of capital A is in the ASCII text? That's lowercase a. Uppercase A, I think, is 65. Right? Well, that's base 10. If you were to encode this in binary, what would it look like? 64, 32, 16, 8, 4, 2, 1. 1, 2, 3. How many bits did it take me to do that? Now, regular old ASCII is technically only 7 bits. Everybody uses 8 bits, though. So this is 8 bits. What about B? B is going to be 66, a capital B. And so it's going to have a fixed length encoding. In other words, all code words have length 8. Okay? Are some code words more common than others? Yeah. Think classic Wheel of Fortune. It's still a show that's on, right? That's where you choose the letters, right? Okay. So what letters do they give you at the end of the show? R, S, T, L, E, is it? Okay. They give you those letters for free. Why? Those are the most common letters, right? Do they give you Z, or would you ever want to guess Z? No, because that's the least common. So if we've got letters that are more common than letters that are less common, why do we have a fixed length encoding scheme? Why not instead have a variable length encoding, where common letters get shorter code words and rare letters get 0 or get longer code words? And what if I'm trying to encode a text file that never even has Z in it? Right? You can also omit some code, some characters. Right? If you have a text file that's just a bunch of DNA sequences, A, G, D, T, C, and maybe some white space or whatever, right? You don't need to encode all 26 characters. You only need to encode what's actually there. So you can omit some characters and throw them out of your code entirely if you need to, if you want to. Right? What this does is basically this reduces the average code word length. Up here with a fixed length encoding, the code word length was always 8. The average code word length is always 8, regardless of whether or not we use it or whether or not one's more common than another. Let me go ahead and give you an example, a small example, of a variable length encoding. Right? Let's go ahead and go with 0, 01, 101, and 010. All right? There is a variable length code. There's one code word that only has 1 bit. There's another code word that has 2 bits. The other 2 code words have 3 bits. Well, what's a problem with this? What if I sent you, here's my message. I'll go ahead and identify these with A, B, C, and D. All right? Here's my message, 0, 1, 0. Decode that. Well, that corresponds to D, right? Is that the only possibility, though? What else could it do? What else could I have sent? What might I have meant to send? A, and then what? Oh, sorry, B, and then A, right? Because otherwise, there's no code word of 1, 0, right? So I sent a B, that first part, and then I sent an A, right? And so you could do it this way. There might be, so in other words, it's ambiguous. So what do you have to do to make it, to disambiguate it? You have to put in a delimiter, right? And say, here's one code word, here's one code word, here's one code word. Right? You can do that, but then that blows up your code. Now, between every single code word, you have to put in a third character, or you basically have to encode that third character, and then you're back in binary. Say that I added a comma instead of A, B, C, D, and then a comma. I'd still have to encode that, right? And then I'd be back at square one with ambiguous decoding. So what I want, my goal, is to find what's called a prefix-free code, right? Where no code word is the prefix of another. As an example, A is a prefix of B, because 0 and then versus 0, 1. What else is a prefix? B is a prefix of what? Of D, right? And that's the only prefixes, right? Why didn't we have this problem with ASCII? ASCII has a fixed length encoding. If I always have 8 bits, 8 bits, 8 bits, 8 bits, can that ever lead to a prefix? No. All right, so that's one reason that we use fixed length encoding over here. For a different application, though, if we want to use a variable length encoding scheme, then we're going to have to make sure that it's unambiguous. And the way that we do that is by having a prefix-free code. Right? Okay? So here's the idea. We're going to say that we want to encode a file. We want to encode a file using a variable length prefix-free code that minimizes the average code word length. Why might you want to do this? What am I doing? If I'm taking a large file and I'm encoding it in a smaller code, what am I doing with this? I'm compressing it, i.e., I want to do compression. I think that's how you spell it, but whatever. Compression. And I'm doing a lossless compression scheme. Because when I decompress this text file, I want to make sure that I can actually read it and that it's not just a bunch of gibberish. There are plenty of other alternative compression schemes out there. For example, what's a compression scheme for music? Music files. MP what? MP3s? That's old school, right? What else, what's there now? What's better? Oh, what? Oh, FLAC's better? Okay. Less loss, okay. I'm thinking more open source. OGG? Nobody's ever heard of OGG? OGG? OGG Vorbis? All right, I think that's even better, isn't it? I don't know. It's better in that it's unencumbered with copyright protections. MP3, I think the copyright ran out on that a couple of years ago. The copyright holders to MP3, you can own a copyright on an algorithm, basically. They never went after like consumers or anything, but they would go after Microsoft, or they would go after big companies with deep pockets and say, you need to pay us if you're going to have an MP3 player, right, on your system. So those are lossy compression schemes. What about images? What's one? BMP, bitmaps, or GIFs, right? Not GIFs, but GIFs. Those are lossless. They encode it, and that's why they're very large. PNGs and JPEGs, those are lossy compression schemes. If you crank up the compression, you get a smaller file, but what happens to your resolution? It gets all fuzzy, right? You're losing information there. This is a lossless compression scheme. We do not want to lose any information, because would it make sense if you took a paragraph and you deleted every other letter? Could you read that very well anymore, right? Or if you deleted every 60% of the letters, right? Then you're definitely getting compression out of that, but are you going to be able to read it? No, right? So this is what I want to do. And our goal for the rest of the day is to develop this, something called Huffman Coding, that does exactly this. Right? The idea is that high frequency, that is common letters or symbols will get encoded with small code words. And the flip side of that is that low frequency or rare letters will get longer code words. Okay? And we're going to want to make sure that it is a variable length, that of course is implicit here. We're going to want to make sure that it's prefix-free, right? And that it minimizes the average code word length. Okay? So here's the idea. We're going to compute, first of all, we're going to assume that we've computed the frequency. Anybody can do that. That's a CS1 thing. You go through and you a file and you count up the number of A's, you count up the number of B's, you count up the number of C's, and then you divide by the number of total characters in that, and you get that 60% of my letters are A's, and 10% are B's, and 5% are C's, or something like that. Suppose that you're given the frequency as input, right? So given a frequency, or frequencies, we're going to build a tree, right? We're going to combine small frequencies as children to a new root node, giving you a new tree. Right? And we're going to continue until one tree remains. Once we've got that, then the path from the root to any leaf defines a code word. Right? That's the outline here. Let's actually look at a concrete example, and then we're going to develop the pseudocode together. Okay? There you go. All right. And I'm going to want a pencil here because I'm probably going to want to erase. But here are the frequencies. It's going to be just a small example. It's not going to be a real file or anything. Suppose that we've got A, which is 10%. 0.10 indicates that it's 10% frequency. B, say that that's 15%. So 15% of all characters are B's. C, D, E, F, and G. All right, suppose that this is an input file. C is our most common at 34%. D is our rarest at only 5%. 12%, 21%, and or sorry, G is our rarest one at 0.3%. Okay? So what I'm going to do is I'm going to start out by making each one of these things its own node. And visually, I'm just going to do that by drawing these as a bunch of boxes. Each one of these is a single node tree. So if I've got 7 of them, a collection of disconnected trees is called a forest, exactly. Right? A collection of connected trees, do you know what those trees are called that all grow together and so they're one big giant organism? No arborists in here, apparently. I think they're mangroves, right? Something like that. Anyway, I've got 7 trees here, small forest. So what I'm going to do is I'm going to take the smallest frequencies and I'm going to combine them first. What are my smallest frequencies right now? D and G. So let's go ahead and combine them, D and G. And I'll rewrite them over here, 0.05, or let's go with the smallest one on the left and the largest one on the right, just to be consistent. It's not going to matter at the end of the day. It's going to lead to an equivalent code, but I do want to be consistent about it. Here's D, and its frequency is 0.05. So if I combine these into one tree, then the frequencies are also combined. The frequency of 3% and 5%, the combination here is going to be 8%. Right? This is a left tree and this is a right tree. Right? And now these are gone. Right? Now I have 1, 2, 3, 4, 5 single node trees, but I have this new 6th tree over here that consists of 3 nodes. So I continue. What are my now 2 smallest frequency trees? Well, there's 0.8, there's 10%, 15%, 34%, 12%, and 21%. So which are my 2 least frequency ones? A and this one over here. So I combine those as well. A, 0.10, and I'm putting the less frequency one on the left-hand side as the left child, and this one over here, the larger one as a right child. Again, it doesn't matter, but it does matter if you want to be consistent about it. Okay. How many trees are left? 1, 2, 3, 4, 5. So on each iteration of this algorithm, I'm taking n trees, combining 2 of them, giving me n minus 1 trees. When do I stop? Well, when I've only got 1 tree. Okay. All right. Let's look ahead here, see if I'm just drawing myself into a corner. I didn't print that out, so I don't know if I'm drawing myself into a corner here or not, but that's okay. Now, which ones do I combine? Well, there's 12%, 15%, 21%, 34%, and 18% now. So which ones are my least frequency ones? B and E. So I'll go ahead and combine them. E on the right, the left child, and B, the right child. And when I combine those, then the combined frequency is 0.27. And now those are gone. All right, I've got 1, 2, 3, 4 trees left. Which ones are the smallest ones now? Well, now it's 0.18 and 0.21, so I'll combine those. F 0.21 and this one over here. And now I've got 39.39. And F is now gone. Now I'm down to 3 trees here. Which ones do I combine now? 27 and 34. So C 0.34. Combine those. And I've got 61.61. Right. And now, unfortunately, I could rip this page in half and put it over here. But that's okay. Should redraw. I should have put this one over here. But I'll go ahead and draw it like this. It leads to an equivalent code. Right? And what do I have at the top? 1, 0. Okay? Now, as a last step, what is my encoding? If I take go to the left child, I'll encode that as a 0. If I go to the right child, I'll go ahead and encode that as a 1. So 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. All right? Let me give myself some more room over here. And let's start enumerating all the symbols. Symbol A, B, C, D, E, F, and we did have G. Right? Yep. All right. Well, what's the encoding for A? Where's A here? It's right there. You'll note here that where are all the symbols? They're all what? Leaves. Right? So the unique path from the root to any leaf, that defines a code word. So 1, 0, 1. And this is the code word. The length, well, the length is 3. Okay? And let me go ahead and repeat the frequencies over here. The frequency of this one was 0.10. What about B? Where's B? Right there. So 0, 0, 1. Its code word length is 3. Its frequency was 15. Where's C? Where is it? C is going to be 0, 1. Its code word length is 2. It was 34%. D is way down here. It's going to be 1, 0, 0, 1. And that's going to be of length 4, 0.05. E is right over here, 0.12, and it's got 0, 0, 0. And a code word length of 3. F is right here. It's going to be 1, 1, 0.21, and it has a code word length of 2. And G is way down here, 1, 0, 0, 0. Code word length of 4, and frequency of 0.03. Okay? There's our tree. I'll leave it over here for a second. Did we improve? Well, first of all, did we reach our goals? Is this a variable length encoding? Yep. Is it prefix-free? Do any one of these codes appear as a prefix of another? Yeah, it's prefix. No, the answer is no, it is a prefix-free code. Why is that? A code word corresponds to the unique path from the root down to any leaf. As we've said, how many paths are there in a tree between any two nodes? Exactly 1. Right? It's unique. Likewise, because of the property that we started out with all of the code words as single node trees and combined them, we ensured that all of these code words were going to be leaves of the tree. Right? If we had an internal code word here, then we would definitely have a prefix somewhere. Right? Like if this one corresponded to X, then it would only be 0, while 0 is a prefix of a lot of these things. So by making sure that symbols only appeared as leaves, that ensures a prefix-free code. Did we minimize the average code word length? Right? A proof of that is beyond the topic today, but let's just do some math here. What's our average code word length? Right? So your average code word length is simply going to be the length times the frequency. So 0.3 plus 3 times 0.15 is going to be 0.45 plus 2 times 34, so that's 68, plus 4 times this is 0.2, 3 times this, 0.36, okay, 4.2, and 0.12, right? And this is going to be, I think, does anybody have it off the top of their head? 2.53. There we go. That's the average code word length. That if you were to actually compress this file, then the original, say that there were 1,000 characters before, and you compress it using this scheme, you're going to have an average code word length of 2.53. In other words, 1,000 encoded symbols times 2.53, you're only going to have about 2,530 about that many characters yeah, that many, because that's the average code word length. Did we do better? Well, we certainly did better than ASCII, right? But that's because we were able to get rid of all but 7 characters from the ASCII text table. If we were to do a fixed length encoding, fixed length encoding other than ASCII, how many symbols would we need? If I've got, or how many bits would we need? If I've got 7 symbols here, how many bits do you need to completely define 7 symbols? Could you do it with 2 bits? How many bit strings of length 2 are there? 0, 0, 0, 1, 1, 0, and 1, 1. Is that enough? So how many bits do you need? At least 3. 1, 0, 0, 1, 0, 1, and 1, 1, 0, and then 1, 1, 1, you don't use that. That leads to a fixed length encoding of 3. Did we compress? We compressed it down from a fixed length encoding of an average code word length of 3 down to 2.53. How much did we compress? Right? You can do that by taking the difference, 3 minus 2.53, divided by the original 3, and this is going to be 15.67%. This is our compression ratio. When you do it, when you zip up a file, does it tell you you compressed it 20% or something like that? Certainly you can take it, and if it was 50 megabytes before and it's been cut down to only, say, 25 megabytes, that's a 50% compression ratio. You cut it in half. Right? This toy example here was only cut 15%. In practice, though, if you use Huffman Coding on English language text files, then you can get compression ratios of up to 40, 50, even 60%. And if you use Huffman Coding on things that are not English, or that are not human readable, say like XML files, where you've got tags that are repeated over and over and over again, then you can get even more compression, better compression ratios. If you do it on, say DNA, right? You don't need ASCII text DNA, AGCT. You can encode that directly in binary and cut it down greatly, right? Rather than some human readable format, right? So this is Huffman Coding, and it's something that you will program on your second assignment. If you want to, you can compare it to an actual program called PAC. PAC is straight on, I think it's installed on CSE. That's straight up Huffman Coding, lossless compression. It'll report the compression ratio for you. Right? So you could use it as a general rule of thumb of am I getting similar compression ratios? Zip is not Huffman Coding. Zipping up a file uses something called ziv-limpel compression. And it's basically an abstraction, or it's an abstraction of Huffman Coding. Whereas Huffman Coding looks at a single character at a time and its frequencies, ziv-limpel considers chunks of characters. So like that XML file where you've got, say, a person tag repeated over and over again, it would see this person tag repeated 50 times, and it would say, I'm going to treat that as one symbol, right? And then I'll encode that one symbol instead. So it looks for strings that can be encoded as directly in binary instead. And so it takes this idea a step further. It's still lossless, but in practice it's much better. And that's what actually is used in zip files, ziv-limpel or LZW, or I forget the third acronym on that. All right? That's Huffman Coding. Let's go ahead and write the pseudocode, since you will be writing, or you will be programming this. As I said before, we'll assume that the input is already given to us as a frequency. So we're given an alphabet of symbols, sigma. We're also given a frequency of symbols. So the frequency of it goes to, say, well, positive reals, right? So in other words, the frequency of x is equal to the frequency of the symbol x in the file. And hopefully everybody would be able to do that. You can open up a file, count the number of characters in there, use a map or something to count the number of A's, count the number of B's, count the number of C's. And you can use a map here to, given a character, what frequency does it map to? Okay? In fact, I've assigned that before in CS1. Our output will be a Huffman tree. That's for this pseudocode over here. Of course, with your programming assignment, your output is going to be a table of code words, along with a report of your compression ratio. So how do you, if I gave you a tree, how would you produce these code words? Well, you could start at any leaf and then go back up to the parent and prepend, so it'll be 0, 0, 0, 0. Right, you're prepending each character that you're going up depending on left or right. You could do an in-order traversal, keeping track of a code word. Right, or do a pre-order traversal, say 0, 0, 0. I see a leaf. What do I have so far? 0, 0, 0. Output it. Backtrack. Now I've got, what do I have so far? 0, 0. Go right. What do I have so far? Oh, 0, 0, 1. Output it. And when I see a leaf. Right? Do a pre-order traversal, in-order traversal, whatever. There are lots of ways that if I gave you this tree, you would be able to go through and enumerate all the code words. Okay? So we're just going to assume that we've created a Huffman tree out of this. Right? Let me go ahead and create a data structure here. Right? Let me go back to this first of all. What did we do the entire time? This is basically a pool of trees. Initially, I started out with 7 trees. And then as I started combining them, I had 6 trees, 7 trees, 3 trees, 6, 5, 4, 3, 2, 1. And then I stopped, right? Each time I pulled out 2 trees of minimum frequency. Is there a data structure that's going to help me find the 2 minimum values? You could go through and just do a linear search. Here's give me the minimum. Well, that's smaller, so okay, update that. That's not smaller, not smaller, not smaller. Oh, that's even smaller. Okay, go ahead and do that. That's the naive way of doing it. Is there a smart data structure that I can put a bunch of stuff in, a bunch of tree nodes or trees or whatever, and I can pull out the minimum value. The next time I'll pull out the next minimum value, combine them, throw it back in. Put stuff in, take stuff out. Such that every time I take something out, I'm taking out the minimum. Is there a data structure that will help me on that? Any? A minimum heap, right? Min heap. Right? Or a priority queue, which is implemented as a heap, right? So we've got a new min heap here. And all we're going to do is put stuff in and take stuff out. So let me go ahead and do an initialization. So for each symbol x in my alphabet, I will create a single node tree. Single node tree. And I will also define the weight, not the frequencies, but the weight of this tree to be frequency of x, right? Just like I did before. And then I will go ahead and insert this tree into the heap here. That's what I did when I drew all of these over here. I initialized single node trees, I associated them with a frequency, and then I put them into a heap for consideration. Right? Now, when did I stop again? I pulled out one, I pulled out another, I combined them, I threw it back in. I stopped when what? When I had 1 tree. So while the size h.size, say, is strictly greater than 1, continue doing that. Pull out one, pull out another, pull out the minimum, combine them. So t sub r, here's my new root. T sub, I shouldn't call it r though, should I? TP, there we go. That's the parent, right? That's the new root. I'll go right and left. H dot get min. Pull it out of that heap. H dot get min. Once I've pulled this one out, then it's gone. It's out of the heap. I will pull out the next smallest one. And then what I'll do is I will combine these, right? TP dot left child. I'll assign that a value of the, wait, I want to do a left first, I guess. That's how I presented it, but again, it doesn't matter. I'll go T sub L, TP dot right child. That'll be T sub R, right? And unfortunately, I've run out of room, so I'll go ahead and continue up here. All right. Once I've combined those two, then I've got my new root node. So I need to define the weight of that. The weight of T sub P is going to be equal to the weight of the left tree plus the weight of the right tree. Right? Just like I did over here. Once I combine them, I pulled them out. Once I combined them, I simply summed up the weights of each one of those trees. I took out the weight of this tree and the weight of this tree, and I summed them up. And that was the weight of my new root. Then I'm going to go ahead and put it back into the heap. So h dot insert T sub P. And that's the end of the loop. And then I'll output h dot get min. Once it's reached a size of 1, it escapes out of this loop, and there's still one thing left in the heap. That's my root. That ends up being, where's my picture? That ends up being this one right here. And it's all connected. Now you can do your tree traversal, you can do your in-order traversal, post-order traversal, whatever it takes to enumerate all of those code words. Right? Really quick analysis here. Right? So the initialization phase, that's of course going to be, well, that's not what's going to be our focus. Our focus is over here. How many times does this while loop execute? Excuse me. How many? N minus 1. All right. Why? Because if I start out with n, this might be the end of the day. If I start out with n, and I go until there's only one left, there it passed. Then I'm doing it n minus 1 times. Now, what's the elementary operation here? You pull something out, you do a bunch of stuff with it, you do an addition, and then you insert it back in. If you want to look at addition as your elementary operation, that's fine, then this is going to be linear. But is this free? Get min, is that free? Get min, is that free? Insert, is that free into your data structure? Nope. What is the cost of these? Get min, then this is review, and insert. What's the cost of that? That's order D, right? Where D is order log n, where n is the number of things in the tree. It's order D, with D is with respect to the depth, but because it's a heap, we've got to guarantee that it's logarithmic because of that fullness property, right? And where n is the number of things in the not in the tree, in the heap. There we go. So on the first iteration, how many things are in the heap? iteration. Again, we're ignoring this initialization phase here. On the first iteration, how many things are in the heap? Iteration 1, size of h, and then get min slash insert cost. How big is the heap on the first iteration? How many things are in there? How many trees are in there? N. So the cost is going to be log n. On iteration 2, now how many things are in the heap? Remember, we're going down. There's 7 things in the heap, then there's 6, then there are 5. So n minus 1, log of n minus 1. On the third iteration, n minus 2, log of n minus 2 is our cost. Right? Our cost is going down, dot, dot, dot. On the ith iteration, how big is it? N minus I minus 1, plus 1, whatever, minus I plus 1, who cares about that? Log of n minus I, right? Dot, dot, dot. On the last iteration, there are going to be 2 things in there, and so the cost is going to be log of 2. I'm not going down to the last iteration, on the n minus 1th iteration, sorry. There are going to be 2 things left in there, n minus 1. We don't go to the nth iteration because that's when we escape the loop. Right? Its size is 2, and then once its size is 1, that's when we escape the loop. So what's the total cost here? Total cost. It's going to be the summation of I running from 2. Here, I'll go ahead and change this to k. K running from 2, 3, 4, 5, all the way up to n of log of k. And again, as a review, hopefully this looks familiar because this is exactly how we analyzed heap sort. Right? This is equal to, I'm just going to rewrite it like I did over here. This is log of 2 plus log of 3 plus log of 4 plus dot, 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 log of n. Log identities. Log of A plus log of B is equal to what? Is what? Log of A plus log of B is equal to log of AB, A times B. If I apply that to all of this stuff, what do I get? Log of 2 times 3 times 4 times dot, 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 n. What is this thing right here? Log of n factorial. All right? Now, factorials are huge, and just like with the number of permutations, factorial, you don't want to do that in practice. But if you take the logarithm of a huge number, guess what? It becomes not so huge. This is less than or equal to, you can use Stirling's approximation on this if you want to, or you could just put an upper bound on this. What's the largest value here? N. So what if I changed all of these to n? N times n times n times n. That would be n to the n, right? Log of n to the n. And now another identity here. What can I do with this n? I can take it out front here. So this algorithm is going to be n log n. Very similar to heap sort. In fact, it's the exact same analysis as heap sort. All you're doing is using a heap to put stuff in and take stuff out. You are exploiting the structure of a heap because it gives you the minimum, and it allows you to arbitrarily, not arbitrarily, but just insert stuff and at a cost only of that's logarithmic because of the depth, because of that structure. Right? So this allows us to efficiently encode stuff. Where's my? Oh, you're over here. This allows us to do this efficiently. This entire thing over here is going to be order n log n. This is also going to be n log n, but they're separate, so twice over n log n is still going to be theta n log n. All right, any questions? Yeah, go ahead. How do you decode it? Oh, if you have a tree, you mean? This is more of an engineering question. If you're actually going to do this, right, you'd have to put in metadata at the front. And this is what pack does. It creates a compressed file, but at the front, up at the top, as metadata, it says, here's my encoding, and then here's the encoded part. And so that if you've got a decoder, it processes this metadata up here and says, okay, that's a code word, decode, decompress, inflate, whatever you want to call it, right? And so this table right here has to be part of the compressed file. Right? And that's just going to be constant overhead for the file. Unless it's like if you can get compression that is actually larger, right? What if I had a file that was just the letter A repeated 1,000,000 times? Repeated 100 times. If I ran pack on that, I might end up with a larger file because the metadata required to say that this is a pack file, it's encoding, it might actually be larger. In fact, you can exploit this idea. Have you ever heard of a zip bomb? No, it's a zip file that seems small, and then when you go to inflate it, what happens? It fills up your entire hard drive. Because it's basically, here's a zip file, 50 trillion zeros have been encoded in this file, right? So, just as an example. Well, that's a really small file, right? Because all it says is, well, here's a 0 and repeat that 50 trillion times. And so when you go to inflate it, you don't know that. And it fills up your hard drive, and that's a zip bomb, right? And it can bring servers down. If you upload a zip file and then the back end, they unzip it unknowingly. That's why try to find a zip bomb and try to deflate it on CSE. Most utilities will try to detect this stuff and say, no, you can't do that. It's a zip bomb. It would end up, they'll pre-compute and say, the resulting file would be way too large. Are you sure you want to do this? And on CSE, you might be able to do it, but you're just going to fill up your disk quota, and then it's going to kill the process. Those are zip bombs, right? And so you can do that. Right? Any questions? Okay, then we'll go ahead and continue there tomorrow with more trees. We're going to be looking at balanced binary search.